Okay, so the last lesson you learned how to tell if the surroundings were going to get hotter or colder based on the sign of a heat of reaction, and then also how to tell how much heat specifically would be absorbed or released by a reaction when given a particular amount of grams. So, one example for you of how we can then take this a step further would look something like this. If 20 grams of chromium are used in the above reaction and the heat absorbed or released is exchanged with 2000 mils of water at 80 degrees Celsius, what is the final temperature of the water? So there's part of this problem that is exactly what you learned last class, and then part of it we're going to extend. So what you learned last class was that for 20 grams of chromium, we can find the heat absorbed or released. Let's see, in this case, because the heat of reaction is positive, the heat is going to be absorbed by the reaction. We just have to figure out how much. So taking the 20 grams of chromium and turning it into moles, molecular weight of chromium is 52. 20 divided by 52 gets me approximately 0.385 moles of chromium. So we know that because of the heat of reaction, we would get 2,256.8 kilojoules absorbed if we had, because of the coefficient, 4 moles of chromium. But we're going to find out how many kilojoules we can absorb if we have 0.38 moles of chromium. So I will cross multiply to solve this. And I'm just keeping the 0.38, that whole number in my calculator. So that's why I'm getting the numbers I'm getting. If you round a little bit, your answer might be slightly different, and that's okay. But cross multiplying, I ended up dividing by that, or here, I'll show 4x equals 868. And when we divide by 4 for x, we get 217. So that 217 represents the kilojoules absorbed, and I'm going to go ahead and say by the reaction, which hopefully from last class, you know, means that the surroundings, in this case, the surrounding water, is releasing 217 kilojoules. So it will be released by the surroundings. In this case, the surroundings are water. Now that we know that, I'm going to go ahead and cover all of this up so we can keep going with the new part of the problem. We know that the water is releasing 217 kilojoules of heat. That's a Q. So we've learned Q equals mCp delta T. It's amount of heat. So that would be a Q value. We also know the 2000 milliliters means that we have 2000 grams of water. That's an M, a mass. And then the T, the initial temperature is 80. But this actually, I say it's something new, it's not that new. We have Q equals mCp delta T. We know our mass is 2000 grams. We know the CP of water is 4.18 joules per gram degree Celsius. So before I can plug this in, always I need to turn it into joules. But then that'll be able to plug in for my Q. And I'll be able to solve for a delta T. So you can use King Henry if you want. King Henry died by drinking chocolate milk, I believe is the most popular one. We're at kilojoules. 1, 2, 3 to the right will get me joules. So 217,000 joules can be plugged in there. So really, we're combining the proportions we learned before with the Q equals mCp delta T stuff from even before that. 217,000 divided by 2,000 and dividing by that 4.18, we get a delta T of 25.96 degrees Celsius. Now, going back, what is the final temperature of the water? Well, it starts at 80. And because it is the water is releasing heat, I'll walk through the logic on that again in a second. But because we know the water is releasing heat, that's why I wrote it out when I did. When you release heat, you get colder. So if we start at 80 and we get colder by 20, I'm just going to say by 26 degrees for ease, 80 minus 26 degrees gets me 54 degrees Celsius. Okay, maybe the math on that made sense, but I want to make sure the logic makes sense. The logic has to make sense, or I promise like you're going to get overwhelmed this unit. So take the time now to make sure it makes sense. This reaction that we started with at the very beginning has a positive heat of reaction. That means that reaction absorbs energy from its surroundings. Apparently, there's some water nearby. And so the reaction is absorbing heat from that water, which means the water must be releasing the heat. And if water is releasing heat, its temperature is decreasing, going down. Okay, I'm going to show you another example in just a moment. Okay, looking at this example, this one might feel a little backwards, but actually has all of the same components as that last example. We have a reaction and a heat of reaction, and we know that water nearby is changing temperature. So how many grams of calcium chloride must dissolve in 50 mils of water in order to raise its temperature from 25 of the water from 25 degrees to 30 degrees? So in this case, we can't start with that proportion that you're used to because we don't know anything about how much calcium chloride we have. This problem is backwards in that sense. So if you wanted to try starting with the proportion, you'd say, normally we find moles and then we plug those moles into the proportion, but I can't. So I'm gonna put that on hold. Instead, let's go look at the water and see if I can do anything there. So I have 50 milliliters. It's water, so I know the CP. And remember that 50 milliliters is the same thing as 50 grams for water. And we're raising the temperature from 25 to 30. So that's a change of 5 degrees. Because I have my grams, my CP, my delta T, I can actually start this problem by finding the heat that the water either absorbed or released. Q equals mCp delta T of the water. The mass of the water is 50. The CP of the water is 4.18. The delta T of the water is 5. Everything I'm using in Q equals mCp delta T is always about the water when we're talking about these problems with some reaction happening and the heat being absorbed or released by water. Always, 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 the Q equals mCp delta T is about water. 50 times 4.18 times 5. We get 1,045. And this is joules because the 4.18 value is in joules per gram degree Celsius. That is the heat. Let's see if it's absorbed or released by the water. Well, 25 to 30, temperature is going up. Therefore, this heat was absorbed by the water. And if the heat was absorbed by the water, we know that that water is getting the heat from the reaction. So we could say that it's 1,045 joules released by the reaction. In this case, it's a dissolving reaction. Now we have enough information. It's going to feel different, but we have enough information where we could go and do that proportion because I know other things about this reaction, the calcium chloride dissolving. I know that 82.8 kilojoules would be released if I dissolved 1 mole of calcium chloride, right? The heat of reaction, the coefficient of the calcium chloride. And hey, my logic holds up here too. We said the reaction should be releasing heat because the water was absorbing it, but also the heat of reaction is negative, so the reaction should be releasing heat. As long as I keep my units consistent, kilojoules released, moles of calcium chloride, sorry, these are overlapping, well, I can use that 1,045 in this proportion as long as I turn it into kilojoules because we already know it's released by the reaction. So moving the decimal 3 times, 1.045 kilojoules is what the reaction is releasing. I'm going to erase some of that so it's not so darn messy. And now this gives me enough information where 3 of the 4 things in my proportion are filled in. I can put an X there and solve for the moles of calcium chloride. Notice I didn't put the negative in front of the 82.8. The word released tells me that. So I should never have any negatives in my proportion. 82.8 times x equals 1.045. Divide both sides by the 82.8. And I would get my x to be 0.0126, and that's moles of calcium chloride. What does the question want from me? It wants grams of calcium chloride. Grams of calcium chloride equals moles of calcium chloride times the molecular weight of calcium chloride. 40 plus 2 times 35.5. My molecular weight of calcium chloride is 111. Multiplying those two together, I got 1.4 grams. So this one is backwards, but has all the same components. A nice overview for you. Everything in the proportion has to do with the reaction. And our units should always be kilojoules. Everything in Q equals MCP delta T has to do with water, and our units are always in joules. So you'll always have that crossover in between.